Here's our first partial fractions example. Integrate x over x squared minus 6x plus 8. We're integrating a rational function of x where the degree of the numerator is smaller than the degree of the denominator, and where the denominator can be factored fairly easily. We like that when it can be factored fairly easily. What we would like to do this integral is we would like to rewrite this fraction in another way. Break it into pieces, break it apart, partial fractions. It's really the reverse of fraction addition and subtraction, where you get a common denominator. We're going to undo that. How? Partial fractions, PF stands for partial fractions. We want to write this as some number, call it a, over x minus 2, plus some other number, call it b, over x minus 4. The goal is to figure out what a and b are. We're assuming by writing this that we can do it. We want these to be equal no matter what x is, as long as we're not dividing by 0, but we're going to use a trick to solve for a and b here that will be a little mysterious because of that. I'm going to multiply both sides by the common denominator of x minus 2 times x minus 4. If I multiply it on the left, this is an x minus 2 times x minus 4. I also have to multiply it on the right so that I am compensating. I get complete cancellation on the left, leaving me with just an x. And when I use the distributive property here, I get partial cancellation. Yet another use of the word partial here. X minus 2's cancel, leaving me with an a times x minus 4. And then with the second term, the x minus 4's cancel, leaving me with the b times x minus 2. Now, the most ideal way to think of this, most rigorous you might say, is to expand this right side as something times x plus a constant involving a and b. Set the coefficient of x equal to 1, because that's what the coefficient of x is on the left, and set the constant term equal to 0, resulting in a system of equations on the unknowns a and b. A linear system of equations. You can solve it with matrix algebra. Tell you the truth, that's great, but it takes too long. We are interested in finishing faster. So what we do instead in most circumstances is pick some values of x that make this equation easy to solve for a and b, like 4 and 2, because they make these terms 0. If I replace x with 4, I get 4 equals a times 0 plus b times 2, right? Which is 2b, and therefore b is 4 divided by 2, 2. If I replace x with 2, I get 2 equals a times 2 minus 4 is negative 2 plus b times 0. Negative 2a, and therefore a is negative 1. But wait a minute. X equals 4 and x equals 2 make the original equation undefined. You can't divide by 0. So is this valid? The ends justify the means. You get the right answer. I mean, you can justify this algebraically in a more general situation, but it really does work. This still works, even though these are undefined when x is 4 or 2. By plugging them in here and solving for a and b, it works. We can plug those back up in here and say this entire thing becomes negative 1 over x minus 2 plus 2 over x minus 4. If you're unsure, is this really right? Did I make a mistake? You can always check it by adding these fractions. Let's try that. Let's check it. Add the fractions by getting a common denominator of x minus 2 times x minus 4. With the first fraction, to get that denominator, you have to multiply the bottom by x minus 4. To compensate, you also have to multiply the numerator by x minus 4. Negative 1 times x minus 4. For the second fraction, You have to multiply the bottom by x minus 2. Compensate by multiplying the numerator by x minus 2 as well. Simplify. Negative x plus 4 plus 2x minus 4 all over x minus 2 times x minus 4. Lo and behold, the 4's cancel. 2x minus x is x. There we have it. That checks it. That is the same as this function that we're integrating here, the function that I put over here. It worked. What's the benefit? I hope looking at this, you think integrating that looks easier than integrating that. Yeah, we're going to get logarithms, ln. For example, if you were going to integrate 2 over x minus 4, you'd let w be x minus 4. dw would be dx, and you'd be integrating 2 over w. 2 times the natural log of the absolute value of w plus c. But w gets replaced then by x minus 4. Something similar happens with the first one. So this integral becomes this integral. And that integral you can just do in your head. Negative natural log of the absolute value of x minus 2 plus 2 times the natural log of the absolute value of x minus 4 plus c. We're done. That's the answer. Leaving it like that is fine for the purposes of the gateway. We will see later in this class when we talk about differential equations, maybe I'll even talk about it a little bit on Wednesday, that it's sometimes nice to rewrite this using properties of logs, bring the 2 up in the power there, and the minus sign means we got the difference of 2 logs, we can write a fraction. We could also rewrite this ultimately as natural log of x minus 4 squared over the absolute value of x minus 2. I don't need absolute value signs around the x minus 4 because it's greater than or equal to 0. But this part is fine for the gateway. If you check this on Mathematica, I'm going to plug in the original integrand function. The original integrand was x over x squared minus 6x plus 8. There we have Mathematica's answer, which is essentially the same as ours, except Mathematica didn't put the plus c. Mathematica also did not put absolute value signs. It's assuming in both cases you know to do that. Do notice it's writing the 2 minus x and the 4 minus x in the opposite order. That's because the absolute value, it doesn't matter. One more partial fractions example today is to integrate almost the same function, but except I'm going to put x cubed on the top instead of x squared. Well, and let me also rewrite the expanded form. The original function on the bottom was x squared minus 6x plus 8. Oops, x cubed here. But now the degree of the numerator is higher than the degree of the denominator. Don't use partial fractions right away. You've got to use polynomial long division instead first. Maybe some of you, your 5th grade teacher said, you know what? I'm not going to teach you how to do long division because you never need to use it. Well, sorry, you got to use it now. That's probably the main benefit of teaching long division in 5th grade, is so that you can do long division now. In 5th grade, it was with numbers, but now it's with polynomials. We are dividing the bottom into the top, you might say. Put the thing on the bottom right there, put the top right there. This is a lower degree here, a higher degree there. Ask yourself, what polynomial can I multiply x squared by to get x cubed? Oh, that's just x. Then take that partial quotient, you might call it, and multiply times every term here. Put the answer down here. And then subtract. The x cubes will go away. Bring the minus sign through the parentheses. Negative of negative 6x squared is positive 6x squared, and negative of 8x is minus 8x. Keep going until what's left over has a degree smaller than what you are dividing by. This does not have a degree smaller. It's the same degree. So I have to keep going. Multiply x squared by 6 to get 6x squared. So put a plus 6 up here now. Take the 6 and multiply down here. Put the answer here. 6x squared minus 36x plus 48. Subtract. The 6x squareds cancel. Negative 8x minus negative 36x is negative 8x plus 36x is positive 28x. And then we have a minus 48. That now has a degree smaller than what you divided by. We can stop. This is the quotient. And this polynomial is the remainder. What does this mean? This means the original function that we were trying to integrate, x cubed over x squared minus 6x plus 8, is the quotient x plus 6, I'll put it in parentheses for emphasis, plus the remainder 28x minus 48, all divided by the original polynomial we are dividing by, the original denominator in the bottom. X squared minus 6x plus 8. Once again, if you don't believe this, if you're unsure if this is right, you can check it. Let's quickly take the time to do that. Check this. How? By getting a common denominator of x squared minus 6x plus 8. I already have that denominator in the second fraction. I need to multiply the x plus 6 by it to get it in the first expression. If I've done this right, the numerator should simplify to just a plain old x cubed. Let's see if that happens. I've got to multiply first x by every term here, get x cubed minus 6x squared plus 8x. And then 6 times every term gets plus 6x squared minus 36x plus 48. Sorry. It's a bit of a mess. Plus 28x minus 48 all over. Sorry about my bad notation. X squared minus 6x plus 8. Stuff does cancel. The 48s cancel. The 6x squareds cancel. And all these things cancel, right? Because 8 plus 28 is 36. 36x minus 36x is 0. It all simplifies to just x cubed over x squared minus 6x plus 8. So this is right. What's the benefit? Again, I'm trying to integrate this. Well, that's easy to integrate. What about that? Not so easy looking, but partial fractions now comes to the rescue. Take that thing, a linear function divided by this quadratic, which can be factored as x minus 2 times x minus 4. And once again, break it up into pieces. Solve for a and b. They will be different a's and b's than before, because we got a different numerator than before. Same kind of trick as before, though. Multiply both sides by the common denominator, getting complete cancellation on the left and partial cancellation on the right. Once again, you want this to be true for all x. You might as well pick x's that make a and b easy to solve for. Once again, x equals 4 and x equals 2. Don't forget to plug it in the left side. 28 times 4, what's that, 112? Minus 48 is 64. I plugged in x equals 4 right there, where I'm pointing. Plug it in the left side too, get a times 0 plus b times 2, which is 2b. So b is 64 divided by 2, 32. Plug in the other number that makes one of the terms on the right-hand side 0. 2. 28 times 2 is 56 minus 48 is 8. 2 minus 4 is negative 2. 2 minus 2 is 0. This is negative 2a, just like before. And a is now negative 4. 8 divided by negative 2. We're almost there. Hang on. What this all means when you put it all together is that the integral of x cubed over x minus 2 times x minus 4 is the integral of x plus 6. Don't forget about that part. That was the quotient from the long division right there. Plus this fraction, which I've rewritten in this way with a equal to negative 4 and b equal to 32. So I get minus 4 over x minus 2 plus 32 over x minus 4. That integral is now easy to do. 1/2 x squared plus 6x minus 4 natural log of the absolute value of x minus 2 plus 32 times natural log of the absolute value of x minus 4 plus c. Wow. Check it. I'll just copy and paste this other integral and change the x to an x cubed up top. You see a 6x like we have. You see a 1/2 x squared. You see a minus 4 log of 2 minus x. Absolute value, that is the same as the absolute value of x minus 2 plus 32 log of 4 minus x. Absolute value, that is the same as the absolute value of x minus 4 plus c. There it worked. Wow. Feeling pretty good now, right? Feeling pretty powerful. As long as we're careful, we can integrate lots of functions. But wait a minute. Remember, we can't even integrate cosine of x squared or e to the negative x squared without invoking Fresnel functions or ERF. So while this is, yes, good, it's not the end all be all of integration. There's plenty of integrals that can't be done symbolically. So we have to rely on numerical integration, which is the next big topic in section 7.5 and 7.6. FTC is always true, but not always helpful.